Professor Technology Binti Ahmad Ghazali from the School of Chemistry and Environment, Faculty of Applied Sciences, University Technology Mara, Negeri Sembilan Campus, Kuala, Pilah, Malaysia. Next, I would also like to introduce to you all our guest speaker from Indonesia. Our guest speaker graduated with a bachelor's, a master's, and a doctoral degree. She is a committed lecturer with over 10 years of experience in one of the world-class university, which is the Universitas Airlangga. She is a professional in chemistry with expertise in synthesis, design, characterization, and application of silica-based materials. From 2017 to present, she is a lecturer from the Department of Chemistry, Faculty of Science and Technology, Universitas Airlangga. Then, from 2019 to present, she is a researcher of the Supra Modification and Nano Microengineering, as well as Membrane Science and Technology Research Group, Universitas Airlangga. Not only that, she has also published more than 20 publications throughout the past 5 years, including proceedings and journals. Everyone, please welcome Dr. Akustia Widati.
Okay, all right. Okay. Siti, thank you so much for the introduction of myself. You can introduce myself. You read my CV. Okay. If there is a trouble connection with my connection, you can tell me. Okay, it's all right. Thank you so much. Firstly, I want to I would like to thank you so much to invite me to Dr. Syed Ahmad that asked me as our department to give he requires the one of lecture to join in the collaborative teaching in this class, and then I will feel happy. I feel very glad when I can join in this class to talk about the bonding in material. Okay, and then first, excuse me, I want to. Is Dr. Shah in this room?
Yeah, I'm here, Doctor.
Oh, I'm sorry. I can see your name. Thank you so much, Doctor. I'm sorry.
It's okay.
Okay. Thank you so much, sir. This is I'm so happy. Happy.
Thank you for accepting our invitation, Dr. Alfa.
Okay. Okay, now I can start this presentation maybe. Okay, Siti, I can go. Okay.
Yeah, you can start. You may start.
Okay, hi students. My name is okay. Who's disabled participants may sharing. You can I want to share my the host, who is the host here. I cannot share my file. Can you give me access to share my file?
Yes, of course.
Okay. Oh. Okay. Okay. Could you give me access? I want to share my file for my laptop. Is it possible? Or if it's difficult, it's okay. Is the host here?
Wait a minute.
Yes. But is it difficult? Yes, okay. Yes,
Can
thank
Dr.
you
Alfa
so much.
try?
Yeah, it's okay. Okay, I can share my file. Thank you so much. Wait a minute. Oh, sorry. I have to. I'm sorry. Yes. Okay. Could you see my slides?
Yes, Doctor.
Yes.
All right. Okay. Now we will talk about the bonding and material. Okay. This is me, Alfa Akustia. You can call it Dr. Alfa. It's okay. From the Department of Chemistry, Faculty of Science and Technology, Universitas Airlangga. This is my simple CV, my simple curriculum vitae. Okay, I'm specialty in organic material, actually in silicon-based material, silica. I learn more about silica. I make a synthesize modification and then studying about the application of silica-based material. Okay. The moderator have read my curriculum vitae, so I can go to the next slide. Okay, first I want to introduce my campus. Give me time for one slide. This is my campus, so I invite to all of you to when you visit to in Indonesia, you can go to our campus in Universitas Airlangga, located in Surabaya, Jawa Timur. I think 2 hours when you take a plane into Malaysia in Indonesia, in Malaysia to Surabaya, just take 2 hours. So I hope you can see in my campus, okay, and I hope I can visit in UiTM, okay. I hope it will happen, okay. Okay, now talk about the material, talk about the chemical bonding, okay. In this class, in this session, we want to talk about what promotes the bonding. What promotes the bonding, what types of bonds are there, and then what properties are inferred from bonding. 3 points we will discuss in this class. Okay. And then, now, in front of you now, in front of me, there is a table, there is a bag, there is a handphone, maybe like in front of you there is also handphone, also pencil, also pen or book or something. There is it can be occurs because there is a bonding over there, because there is a book, pencil, table, bag, or anything, handphone, notebook, our t-shirt, our trouser, like the others. This material, when we say in the macroscopic structure, if we talk about macroscopic structure, if we talk in the macroscopic structure, it's a structural element that may be viewed with the naked eye. We didn't need we didn't need any equipment to see that. I can see table, I can see bag, I can see my bottle. This is my bottle. I can see it's the other. This is a macroscopic structure. When we want to see in this small area, and we want to see what happened, what is the composition, what happened in the small parts of microscopic structure. This is the name of microscopic structure. Microscopic structure is the arrangement of small grains of material that can be identified. We have to use a microscope. We cannot see that with the naked eye. You can see that if we say microscopic structure. Okay, after we see it in the microscopic, we see in the, using microscope. So we want to know what happened in the smallest of the macroscopic structure. Okay, if we think about that, we talk about the atomic level. The atomic level is the arrangement of atom and material. Atom material can have the atom make arrangement. So like the graphite and diamond. The atom is carbon, but this carbon make an arrangement, they become graphite, they become diamond. In the macroscopic, graphite can be a pencil. Pencil. In the macroscopic, this is the macroscopic structure. This is the macroscopic structure. This macroscopic structure, you can see the pencil. Sorry, microscope. Microscopic structure, we see the pencil. But in the atomic level, you can see this is the graphite. Okay. Graphite is the arrangement of carbon. Okay, and then how the carbon can arrange the other to be a graphite? What happened in this carbon? Okay, and now we talk about the subatomic level. Subatomic level is an electronic structure. Now we talk about the electron, the atom, the small parts of the pencil. Okay, we talk about the electronic structure of individual atoms that define interaction among atoms. This is the interatomic bonding. Okay. When we talk about the interatom, when we talk about the subatomic level, the atoms determine arrangement of atoms. There is an arrangement, there is an electron, okay? There's an electron, there's arrangement of atom to be a some material. So it will happen because there is a bonding. There is a bonding. When I have carbon make arrangement, become graphite. It can be used as a pencil. But we do not talk about the pencil, but we talk about the carbon arrangement. Why it become a pencil? Because there is a bonding. Why it come there? Because there is a bonding. Carbon also can make arrangement become diamond. Okay. Pencil and diamond, both of them is composed by carbon. But why there are same elements carbon, but why it can be one of them is a pencil, one of them is a diamond, okay? Or I can say one of them is become a graphite and one of them is become diamond, because different arrangement is make a different crystal structure. When different crystal structure is happen, of course it will affect the material properties. Graphite is the color is black, and so the hardness is not too hard like diamond. Diamond is too hard, but the application can be as a jewelry, as can be as gems, and yes, but they are harder than graphite. Why it's happened? Because there's a different arrangement and different crystal structure. If we talk about the material properties, it's not only the types, the factor is not only the types of bonding. The composition is also influence the type of bonding. But now our focus is talk about bonding. Okay, we don't talk about the composition. Okay, if we want to talk about the bonding, nice. Why the atom make a bonding? Why the bonding is happen? Because in the natural behavior, atoms want to stable. They want to be stable. It's not only the atom. I, you, and all of participants want to be stable. One in the stable condition, one in the less energy, one in the low energy. Including the atoms. Atoms want to stable. To be a stable, there are one famous rule. There are octet rule. This states that a stable atom contains the stable atom. It must contain equivalence electron. Maybe some literature can write with not only equivalence electron, but have a similar with Nobel gases electron configuration with the completely orbital, but completely electron of orbital. Okay, if there are in this position, if this I'm sorry. Okay. If the atom is the atom in the contains equivalence electron, the atom is will be stable. So to be stable, there are three efforts to achieve the stability. The electron is losing, gaining, or sharing electron. Okay. Now, when we talk about the electron, we always remind about the periodic table of the elements. This is the periodic table of the elements. This is the periodic table of the elements. The periodic table of the elements is the, we can see more than 100 elements, and then this is atomic number. Atomic number is information for us how many electrons that have for these elements. Okay, hydrogen have 1 electron, lithium have 3 electrons, beryllium 4 electrons, and the others. So when we talk about the bonding, we have to remind, okay, this is the periodic table with the electron. Let's see that. Yes. Hydrogen with 1 electron. Hydrogen with 1 electron. Lithium with 3 electrons. Beryllium 4 electron. This is the atomic number. Atomic number is tell about how many electrons that we have. Beryllium have 4 electron. If you configure it, if you write the electron configuration is 1s2, 2s2, that 1s2, 2s2. It is important to us to predict what is the type of bonding that happen in this material. We have to know the electron of each element, the electron of each atom. Right. Yes, okay. After that, after we know what is the position of the atom or element in the periodic table, after we know how many electrons that have for each atom, okay, we can predict what is the bonding, what is the possible bonding that will happen for the material. we want to discuss about the types of bonding: ionic, covalent, and metallic bonding. We discuss about it. Ionic, covalent, and metallic bonding. Actually, I believe that you have ever heard about the bonds. Actually, there are two classifications of bonds: primary and secondary bonding. Okay, and here, when I write here the types of bonding, is this the primary or secondary bonding? I write here types of bonding is primary or secondary bonding.
Primary bonding.
Primary bonding.
Okay, we talk about the primary bonding. To make a material occurs, it's the dominant. The material axis is dominant bonding is a primary bonding. But we have to know actually there are two classification of chemical bonds. Two classification of bonding. There are primary and secondary bonding. What is the difference of primary or secondary bonding? Primary bonding is divided as ionic bond, covalent bond, and metallic bond. And the secondary bonding is a hydrogen bond, van der Waals force, and dipole interaction. The difference between of them is the primary bonding is a sharing or transfer electron. Both primary and secondary is talk about electron. But the difference is between primary and secondary is which one? Primary have a sharing and transfer electron, but secondary no sharing or transfer electron. Because there are in secondary is no sharing or transfer electron, there are weak force interaction. In primary is strong force interaction. Okay. Now we want to talk about the primary bonding. In the secondary bonding, we talk about that in last slide. Okay. Talk about ionic bonding. First is ionic bonding. Ionic. The term is ionic, so it's become a term is ionic. Okay, ionic. The term is ionic bonding, so we want here we talk about ions. Ions are formed when atoms gain or lose electron. Jadi ions is a cations or anions. Jadi ionic bonding is about a cation or anion. It will happen if there is a cation and anion. Cation and anion. When it become cation, when it become cation, where the elements they lose electron. When they lose electron, they become cation. When they gain electron, they become anion. Why the atom have to be cation? Why the atom have to be anion? Let's see about the octet rule. Let's see the octet rule. Octet rule state that the stable atom is have to make the electron configuration is similar with the noble gas or in the egg valence electron. So to be egg valence electron, the atom can be lost or against electron. When it lost electron, it becomes cation. When gains electron, it becomes anions. Okay. Next. The force of attraction between a positive charge and negative charge create the ionic bond. Okay, we have to remind the octet rule. Sodium ion, or maybe that's sodium with the number atomic number 11. I make the electron in the each shell is to be 2 8 and 1. 2 8 and 1 is totally is 11. And then fluoride is the number the atomic number is 9. The electron is 2 and 7. When I total is 9. Okay. It is not a complete. This is not similar with the noble gas. This is not. This is the condition. It's not the octetral. So the sodium to be octetral, they have to lose 1 electron. They have to lose 1 electron. Excuse me. They have to lose 1 electron to become 2 and H. Okay. Sorry, I have to use this pencil. Okay, they lost 1 electron. They lost 1 electron. When they lost 1 electron, they become 2 and H. This is completely electron configuration. Then, because there are lost 1 electron, it become ion, sodium ion. It become cation. Fluoride with the 9 electron. The electron configuration is 2 and 7. 2 and 7 is not octetral. Totally here is 7, but octetral say that totally the electron valence electron is 8, but here is still 7. So they have to gain 1 electron. They have to accept 1 electron to become 2H. Sodium ion that lose 1 electron, they accept the gain in the fluoride ion is accept the electron for sodium to become 2 and H. And now the sodium ion, fluoride ion is completely the octetral. There are half H electron in the valence shell. They have a valence electron, the totally is H. So this is the reason why the atom have to be cation, have to be anion, because they want to be stable. To be stable is the completely the octetral. Octetral is 8 electron, 8 valence electron. Okay. If I have chloride. Oh, it's no. If I have oxygen is 6. I'm sorry. This is we cannot use subscribe in the Zoom. Okay, the atomic number of oxygen is 6. Oh, sorry, H. H, is it right? The atomic number of oxygen is H. So the configuration, the electron configuration is 2 and 6. Or maybe you can write with 1s2, 2s2, 2p4. To be complete, to be stable, they have to have configuration with the electron in the valence cells is have 2 H electron. There is this says have 2 H electron. To be an H electron, they have to, how do you think? They have to lose or gain electron for the oxygen.
Gain
electron. How many electrons that have to gain for oxygen? 2 electrons. 2 electrons. Okay, this is a achievement. This is the effort of element. This is of effort of atom to be stable. Okay, thank you for your active response. Okay. This. Okay, just so when the positive charge and negative charge have interaction each other, they make a force of attraction. it creates an ionic bond. So ionic bond is the clue is there is a positive charge and there is a negative charge. Also, we can say there is an anion and there is a cation. So, when the atom become anion and cation, it's become ionic bond. Thus, cation and anions forming an ionic bond. The electron orbital generally do not overlap. Okay, in ionic ion, the orbital electron is not overlap. The overlap is happen in the type of bonding, the others covalent bonding. But in ionic bondings, do not overlap. There is no overlap. There is no overlap. There's no overlap in ionic bond because the cation. Like this, because the sodium ion is give the electron to the fluoride ion. There is a orbital. There is no overlap orbital because it's about loss and gain. It's about I give you and you accept me. It's about that. Only strong force of attraction. So the interaction is about only strong force is the Coulombic force. Coulombic force is the interaction between plus and minus, between cation and anion. Sorry, between cation and anion. Okay, interaction is not for overlap, but interaction. The attraction is not. Because not overlap, but overlap orbital, but because the attraction, because the Coulombic force. Coulombic force is happen between positive and negative charge. Okay, this is the image. There is no overlap because one of giving the electron and one is accept the electron. Okay, so about the property. The ionic material or the ionic solid conduct electricity, but sometimes we still have a mistake. Some people say that ionic material can conduct electricity. This is not totally false, but it's not also totally true because they will conduct electricity if they have in the liquid phase. If they are in the solid state, there are no conduct electricity. Why? Because when we talk about the electricity, we talk about electron, we talk about a charge, positive charge and negative charge. In the solid state, there are no positive charge and negative charge. I'm sorry. There are no negative charge and positive charge. Oops. Okay. I have to see my. I put the middle. Okay, I'm sorry. All right. When we in ionic material or ionics, we can say ionic solid, we can say ionic material. Some people say that they can conduct electricity. It's not totally false, but it also is not totally true. It's also false, not totally true, because if they are in the solid state, in the solid phase, of course they are not conduct electricity. because electricity, it can be happen if there are a positive charge and negative charge. But when negative charge, but when in the solid state, in the solid state, the positive and negative charge is attract each other to be a neutral charge, in the neutral charge. So of course there are no conductors. Of course they do not conduct electricity, because the positive or negative is each other interact with each other. So there are no positive or negative because the total charge is neutral. So when it happens, when the solid can conduct electricity, they can conduct electricity if they melt in the liquid phase, melt or dissolve in water. Because in the liquid phase, if they melt or dissolve in water, the positive or negative charge is its spirit. The spirit. So we can meet this is positive and this is negative. The interaction is weak interaction, the positive and negative charge. Then if we compare with solid state, of course, in the solid state, the interaction positive or negative is stronger than melts or dissolve in water. So if we want to use the electricity properties for ionic solid, of course, we have it to the liquid phase by melt or dissolve in water. Okay. So if someone say that okay, ionic solid, it can conduct electricity, of course it's not the end of sentence and it's not an end of statement, because we have to continue with okay, can conduct electricity if they are melt or dissolve in water, but cannot conduct electricity when in the solid state. Okay. And then the ionic solid are hard. They are hard, rigid, strong, and brittle. Hard, rigid, and strong. Why? Because ionic solid is the make an arrangement as a crystal. Make an arrangement like a crystal. Crystal. Arrangement as a crystal. Because they make a arrangement structure, arrangement geometry as a crystal. They are so hard. These are hard properties, rigid properties, and strong properties. You can imagine that sodium chloride. Sodium chloride is salts. Sodium chloride. Sodium chloride is about an interaction with the sodium ion and chloride ion. But actually, it's not it's not like that. It's not okay. This is the ionic bonding, and then we see that this is sorry, I have to. This is not an ACl. This is, and the other is sodium and chloride. Okay. If we have a sodium chloride, it's not like this. It's not like this. Okay, there is one ionic bond. This is the other, and in the okay, this is a ionic bond of sodium chloride. In the left side is we see that sodium chloride of the ionic bonding of sodium chloride. In the right side we see that the ionic bonding of sodium chloride. It's not like that. The sodium chloride is interact with other to become a rigid, to become their interaction each other like this. This is the sodium chloride, sodium chloride, sodium chloride. Okay, they make a closely packed. The pack is either they pack to be a crystal. because they make an arrangement like that, so they are hard, rigid, strong, and strong. But why they are brittle? Brittle because when this is because when there is an external force, okay, it's an external force, there are a like charge ripple. So, so we disturb the charge over there. So there is like charge ripple, and then crystal is cracked. So this is the meaning of brittle. Okay. Sorry. Because the ionic solid is make a crystal structure, make an arrangement like that, this crystal structure. They have a lattice energy. They have a lattice energy. And of course, because a structure that like cubic, maybe. Example is a sodium chloride. Sodium chloride is the cubic structure because they form like that. Of course, they have a melting points with the high melting points. Of course, they have high melting points. Why? Because to melt this ionic solid, we have this is a required high energy to break the bond. Why? Because the arrangement, the structure is to be a crystal. And about the lattice energy is decreased when the size of ion increase. Okay, lattice energy is the amount of energy and required when the positive or negative is interact. When the size of ion is small, of course the lattice energy is of course we have a low lattice energy. Okay, multiple bonding electron increase heating energy. Okay, it's like that. It's similar when the electron with the size of ion is higher, is of course increase of lattice energy. Okay, we have a table like that. You can see the table, the lattice energy and melting point value. We have an ionic solid, lithium chloride, sodium chloride, potassium chloride, rubidium chloride, and cesium chloride. We can see this is in one group: lithium, natrium, sodium, potassium, rubidium, and cesium. This is one group. You can see the lattice energy. Okay. And then you can see that the melting point. It's similar with this. You can compare it. So this is the reason why when we have an ionic solid, they have a melting point. Yes, because this because they form this, because they form structure like this. The structures like this make a high melting point, high boiling point, hard, rigid structure, but also is brittle. Okay, now we talk about the covalent bonding. Covalent bonding. We talk about the covalent bonding. Here I want to, we can see this is the covalent bond and ionic bond. We compare covalent bond and ionic bond. Covalent bond is about the sharing of electron, but in ionic bond is about the transfer of electron. Ionic bond is a positive ion. Okay, I give you electron to negative ion. I give you electron. Okay, I accept your electron. This is the ionic bond. But in covalent bonds, the mechanism is not similar with ionic bond. The mechanism, no accept, no give and accept, no lose and gain, but the sharing of electron. They use together. They use electron together. This is a covalent bond. And in the covalent bond, there is an overlap orbital, overlap electron, because there are sharing of electron. But in ionic bond, there are no overlap orbital. The interaction it's from force attraction, Coulombic interaction, Coulombic force. Coulombic force is between positive charge and negative charge. But the covalent bond, the interaction, the bonding is because the overlap between sharing of electron, because of the sharing of electron. So the image like that. The image is mean the sharing of electron. But in ionic bond, there are no sharing electron. They give one electron to here. So this is loose electron and this is gain electron. But the covalent bond, they use together the electron and form a bond. This is a difference between covalent and ionic bond. Okay, involve sharing of electron. Okay, usually it's between two non-metals. Okay, I have not explained yet the criteria of ionic bond. Okay, a covalent bond is between two non-metals. Usually it's between two non-metals. But in ionic bond, okay, ionic bond, I just explained. But ionic bonding, it's from the interaction between metal versus non-metal. Metal versus non-metal. But when the two non-metals, usually it's happen in the two non-metal for the covalent bonding. For the example is hydrogen, carbon, oxygen, nitrogen, or the others. Covalent bonding, like ionic bonding. What is the meaning of ionic bonding? They want to be a stable compound. Okay, covalent bonding, like ionic bonding. What is the meaning of like of ionic bonding? Like ionic bonding, it means this is the effort. This is the effort for the atoms to be more stable, but in different mechanism. How? In the covalent bonding, we see that not only the single bond can happen, and the ionic bond is only single bond. But covalent bonding, we can meet the single bond, double bond, triple bond. It's possible to happen in covalent bonding, but it's not happen in ionic bonding. Why? Because it's about share electron. Share electron. Ionic bonding, no, there is no double and triple bond. It's always single bond. Why? Because there are not share electron. In ionic bond is about the loss and gain. Of course, loss electron, not only one electron to lose, but maybe two electron or sometimes it's 3 electrons to lose. But the type of bond is always single when the ionic bond. But the covalent bond, because it's not loss or gain, but it's not sharing, a share per electron can be a single, double, or triple. For the example, I have methane, CH4. I have this. Okay. Carbon with 4 electron, with the 4 electron. This is the electron carbon. This is the electron from carbon. They make a bonding with hydrogen, 4 hydrogen, and each hydrogen is contribute 1 electron. This is okay. They use together each electron to be this is a single bond, this is single bond, this is single bond, and single bond. Every bond is involved 2 electrons, because in here there is 2 electrons. This is a single bond. Single bond. Okay. So how many single bond in CH4? How many single bond in methane? So 4 single bond. Okay. What about the mechanism? Okay, the mechanism. Covalent bonding is, when we talk about covalent bonding, we talk about the hybridization. Hybridization. Carbon has electron configuration 1s2, 2s2, and 2p2. Okay, this is electron configuration, and we write it in the orbitals. This is 1s2, okay, completely filled, 2s2 also completely filled, and 2p2. Yes. Indicates carbon forms two covalent bonds, but because we have to, carbon have to interact or have to make a bonding with the four hydrogen, they have to, the carbon have to for empty orbital, empty orbital. In the ground state arrangement, there's still two empty orbitals. So what happened? What will happen? What have to do with the carbon to have for empty orbitals? So, and then hydrogen can fill to the electron of carbon, orbital of carbon. Carbon do hybridization. Hybridization causes one of the 2s orbitals. So hybridization. The hybridization is one electron from 2s is make an excitation here. So they are like this, and resulted like this: 1, 2, 3, and 4. Now the carbon have 4 empty orbitals. It can be used for hydrogen to fill this orbital. This is the mechanism. How about a sharing electron? They create a hybridization. They create they have to some orbital. They have to empty orbital to have interaction with the other elements. In this case, carbon have to more orbital, have 4 orbital for hydrogen to fill this empty orbital. So there are 4 covalent bonds are formed. Okay. This is the covalent bonding. Okay, covalent bonding. Covalent bonding is I want to compare ionic and covalent. If ionic bonding, the structure, the arrangements of ionic bond, it resulted a crystal, resulted a close peak or close peak arrangement. Close peak arrangement. But in covalent bond, it's not. But covalent bond, we still meet the electron jets. For the example, CS1 methane. I'm sorry. For the example, I make a simple example. Hydrogen. Hydrogen is a covalent bond. Let's see. Hydrogen. And the others is hydrogen. And others is hydrogen. There are acids in one molecules. I mean, there are no interaction between the each of molecule hydrogen. There are no interaction. It's different with sodium chloride. Sodium chloride is make a crystal like that, make a solid. So they are hard, rigid, and then yes, solid, rigid, and that thing for ionic bond. But the covalent bond is not. The molecule in the molecules, the presence of the molecule is not interact each other. There are two. But some molecules, some of covalent bonds of a covalent compound can be covalent network solids. Can form the covalent network solid. For the example, like diamond, quartz, silica, or silicon carbide, this is a covalent, but the presence is not individual. It's not individual. It's not like that. The presence with the make a network like ionic solid. Presence like this, ionic solid. They interact with each other to become covalent network. They're repeating particles by covalent bonds. Okay. So if we compare with the, of course, the properties is very strong covalent bonds because they make a network. Of course, this is have a high melting point. Yes, of course, because they make a network, and of course they're hard. And this, of course, the solubility in water, of course, is very low because they make a huge network like that. The name is covalent network solids. Some of covalent compounds is become covalent network solid, but some of them is not form the covalent network. All right, and then the metallic bonding. The third bonding is the metallic bonding. We have to we have learned about the ionic bonding, covalent bonding, and then now it's the metallic bonding. Metallic bonding is, the name is metallic bonding. So of course it's happened in a metal, or some cases in alloy. Metallic bonding. Bonds between atom and a metal held together in a crystalline lattice. Crystalline. So if they talk with about crystalline, is like so it means the structure is network in a sea of mobile electrons. Metallic material have one, two, or maybe three valence electrons. These valence electrons are not bound to any particular atom in the solid and are more or less of rigid. The metallic bond is about the C electron, G electron count. It's different mechanism with ionic or covalent bonding. Ionic is about loss and gain, and then covalent bonding is about sharing electron, but metallic bonding is about electron count. Metallic bonding is strong electrostatic attraction between closely packed positive metal ions. And because there are delocalized as electron. We go to the next slide. You can see the image. Nice. Okay. This is a metallic bonding. This is the core. This is the core of atom. Okay, this is the core of atom. This is the electron. Okay, the dot, the move dot is electron, but the red dot is the core of atoms. The black dot, black small circle of that, this is the electron. This is the sea of electron. This is the name of cloud of electron. You can see that this is the charge is positive and the electron is negative. The interaction between positive and negative, it makes a metallic bonding. Of course, it's only happened in metal. Non-metal didn't have a metallic bonding. Non-metal do not have the metallic bonding. It just happened in the metal material. Okay, this is a core electron, core of atom. This is electron move in any move. They make a movement, make a motion to be a sea of electron, to be a cloud of electron. Because a core is the charge, of course, is positive, and then the electron is negative. So this is an interaction. What kind of interaction? Positive and negative is this is like a column interaction. Okay, this is a metallic bonding. It's specific for metal. Metallic materials have a moderate melting point. They have moderate multiplying. Not same with ionic bonding. The same with the ionic solid. It's not same with the ionic material have high multiplying. Metallic material have moderate melting point. Why? I say that metallic material is also make a network. See, this is make a network. Also make a network like ionic solid. They have positive and negative charge. They have positive and negative charge like ionic solids. But why? The melting point is moderate. Why it's not same with the ionic solid? They have high multiplying because there are no breakage of bonds, because there are no breakage of bonds needed for melting process. In the melting process, there are no breaks of bonds. But in ionic solids, to make a melting process, we have to break bonds. We need a high energy. We require the high energy to break the bonds. But in metallic material, it's not necessary. It's not necessary to break the bonds because there is no bonds over there. Metallic material are soft and deformable. It's mechanically different than ionic and covalent bond material. Metallic material are excellent electrical conductor. Okay, metallic material electrical good in electricity, electrical conductor, due to the delocalized nature of electron. It's different with ionic solid. Ionic solid is also for this point. Ionic solid. Ionic solid, yes, it have a good electrical conductor, but it's not the solid state. But in the solid state, because we have to become electrical conductor, to have a good electricity, we have to ensure there is a positive and negative charge over there. But in ionic solid, especially in solid state, no positive or no negative charge over there. But in metallic material, although in the solid state, they have an excellent electrical conductor. Why? Because there is a electron sea, the sea of electron. Because there is the cloud of electron over there. Because there is an electron, so there are the electrical conductors in the solid state. But in ionic solid, in the solid state, they have no electricity properties, no electrical properties, because there are positive and there is no positive or negative charge. But in metallic materials, in solid state, they still have the electrical conductors, because the nature of electron is present in the sea of electron, the cloud of electron. Okay, the metal are also thermal conductors due to thermal atomic vibration across the metallic body. It's like similar reason with this, because it is about the sea of electron, cloud of electron. All right, now we have the metallic bonding. Okay, we have to learn ionic bonding. We have discussed it. And then covalent bonding, we also discussed it. And then the last is metallic bonding. This is a primary bonding. This is a primary bonding. Metallic bonding is delocalized as electron plus the key point, the key word, the key point of metallic bond is delocalized as electron cloud. Is the point. This ionic, the point is positive and negative charge, cation or anion, loss or gain electron. And the covalent, the keyword is sharing electron. But in the actually there is a covalent, there is a mixed bonding. There is a mixed bonding. This ionic and covalent mixed bonding. It means the material have two character, ionic character or covalent character. Actually, all of the material have a mixed bonding. Actually, if you do some research, you determine, you measure how many ionic ionic character, how many percent of covalent character. Actually, all of the material have ionic or covalent properties. This we can determine, we can measure the ionic character, the percent of ionic character using this formula. Okay. In this, if you want to learn more about that, you can search in the internet. You can search in the Google. You can go to the library or something. You can proceed with the ionic covalent character. This is an interesting topic. And make sure this is an interesting topic because the material, most of the material have two properties, ionic or covalent. For the example, like magnesium oxide, the properties, the character, the percentage of ionic or covalent character, it depends the electronegativity. This is Pauling electronegativity. Actually, there are many value of electronegativity. Pauling electronegativity, Arrel-Kircher electronegativity, Mulliken electronegativity, but the famous is Pauling electronegativity. The famous one is Pauling electronegativity. So many formula, many equation use the electronegativity in the Pauling scale. Okay. Magnesium oxide, we see that magnesium oxide. Can someone answer what is the type of bonding of magnesium oxide? Could you answer it? Ionic, covalent, or metallic bond? For magnesium oxide, how do you think? Solid, covalent solid, or metallic? Ionic. Okay. Yes, ionic bonding. Now, we measure, we determine, we calculate the ionic character in the magnesium oxide. Okay. This equation, this formula, and then the electronegativity of magnesium 1.3, substitute over there. The electronegativity of oxygen 3.5, this is the order. And now the percentage of ionic of character in magnesium oxide is 70.2% of ionic. The ionic is 70.2%. So there are almost 30%. This is the covalent character. For this, we know that magnesium oxide is ionic bonding. Is this ionic compound? Yes, it's right. This is right. For this calculation, this is right. The 70% is ionic. I mean, the dominant of character is ionic. Like our prediction, the magnesium oxide is ionic solid. This is ionic compound. Yes, it's right. But they also have covalent character. This is 30%. This is 30%. So there are no material totally 100% ionic. No, it's difficult to see that. some material, ionic solid, is always have a covalent character. And vice versa, the covalent material is also have ionic character. Okay, so this is interesting. So I recommend you to learn if you have time. Of course you have time, okay? If you have, because you're student, of course you have time to learn. Yeah. You have time to learn about the ionic covalent character. This is so interesting. You can see the application of ionic covalent character. When you do a research, it's more useful. It's useful if you learn. If you understand, if you ever read the theory of ionic covalent characters, you can browse it with your handphone. Ionic covalent character is so interesting. It's actually there are no 100% material is 100% ionic, 100% covalent. This is difficult to see that, difficult to meet it. Some material also have ionic and also have covalent, but always in the dominant. Magnesium oxide is ionic solid. Yes, it's right. The ionic character is so high. Yes, 70%. They have, but they have also covalent character in the small percentage. This is 30%. Like silicon oxide, silica, it have 49% covalent. Correct me if it's not, if I make a mistake. Covalent character, and then 50% covalent character, and then 49% ionic character. They almost have 50-50 covalent and ionic character for silica. So it is a reason for me. I write in my curriculum vitae that as Siti read on my curriculum vitae, but the Siti or in the curriculum vitae in my slide, I say that my interest, my specialty is silica-based material. This is the reason, because silica have covalent and ionic character. So I'm interested to modify silica because silica I can go silica to the covalent, I can go silica to the ion. So the application is wide than the other. Okay. As the summary properties of metallic, ionic, and covalent bond. Okay, this is the summary. For the metallic, this is the high boiling point. Okay, high boiling point, same like ionic, high boiling point. But if okay, similar like ionic, high boiling point, but some literatures state that ionic is higher than metallic bonding. Ionic is number 1, metallic is number 2, and then number 3 is covalent for metallic and boiling point. But anyway, it's always depends on the elements. Depends on what is the compounds, what is the element, what is the type of atom. So it's just the general summary. General summary that ionic is number 1, metallic is number 2, covalent is number 3. I'm not fully agree with this statement, but some literature state like that. Why? Well, why I'm not to agree? Because of course it depends on the kind of elements. Okay, because it depends on the kind of, but covalent is low melting points there. But the covalent in the covalent network, then we can. But covalent bond, if they form the covalent network, of course, they have a high melting point, also have melting point. Okay, this is a general summation. High melting point. If there are make a covalent network. The hardness. Okay, the hardness. The hardness, metallic is hard. Okay, metal is always hard. Ionic is hard because they make a crystal. Covalent is soft because there are no create a covalent network. But if they in the covalent network chemistry, of course, it's also hard. The key point is network. Okay, metallic is always network. Ionic is network, also network. But covalent is two possibility. There are in the single molecule. There are distribute in the single molecule, disperse in the single molecule, or they interact with other to be a covalent network. If there are in the single molecule, of course, the hardness is softness, the melting point and boiling point is low. But if they are in the covalent network, of course, the hardness is hard. Okay, and then conductivity. Conductivity is metallic is in the solid, liquid or aqueous phase. There have high conductivity. Covalent, there are no conductivity in all of phase. But in ionic solid, it's only liquid and aqueous phase, they have a conductivity. No in the solid state. All right. Okay. This is the primary bonds. We have to discuss it. Primary bonds. Now we talk about secondary bonds. Secondary bonds. Secondary bonds is no sharing or transfer electron. This is weak force interaction. Weak force interaction. Why weak force interaction? Because this is intermolecular interaction between molecules. But in primary, its molecule can be happen because the primary bonding. But the secondary bonding, the molecules exist, and between molecules interact. So there is no sharing or transfer electron. And the consequence is the weak force interaction. Okay, secondary bonding is a permanent dipole-dipole interaction, van der Waals force, and hydrogen bonding. Okay. If we make an order, ionic and covalent bond, the strength of the bond strength, the strength of bonds is 100, hydrogen bond is 50, dipole-dipole is 10, van der Waals is 1. Okay, so the weakest one of the bonding is van der Waals force, and then dipole force, and then hydrogen force, and then the last is ionic and covalent bonds. Hydrogen bonds is the strongest bonding in secondary bonding. In secondary bonding, hydrogen bonds is the strong than the others. Okay. But if we want to compare with primary bonds, of course, it's so weak because the primary bonding ionic and covalent have relative strengths 1,000, hydrogen bonds only 50. Okay. This is the comparison between primary and secondary bonding. Okay, permanent dipole-dipole force. For the example, okay, I go faster. Polar molecules have a permanent dipole. It happens in the polar molecules. For the example, hydrogen chloride, it's NCl, hydrogen and chloride. Hydrogen is positive partial. This is positive and partial. So chloride is a negative partial. And the other molecule, they meet with HCl, hydrogen chloride molecule HCl. In the the molecule of hydrogen chloride meet with the other molecule of hydrogen chloride, HCl. They make an interaction between molecules. We talk about molecules. We talk about two molecules interaction. We are not talking about the intramolecule. We're not talking about the internal molecule of internal interaction in molecule. No, but we talk about interaction between two molecules. When the negative partial charge meet the positive partial charge, okay, they have interaction. the interaction is called with dipole-dipole force, permanent dipole-dipole force. Yes. And the second, van der Waals force. Van der Waals force is the weakest force, weakest bonding. Weakest bonding because in the weakest bonding, because the relative strength is 1. Okay, you can see the table, the last table. The van der Waals is only 1. Van der Waals 1. Why? Because it becomes why? Because it's happened in the neutral molecule, like hydrogen. Hydrogen is not the hydrogen not have the dipole. They have not dipole. It's not similar with the polar molecule, have a negative partial charge and a positive partial charge. No, hydrogen do not have like hydrogen chloride, because the electron is distributed in all of distribute in all of this molecule, but it can be a dipoles. It can be a dipoles when it moves, when more it moves, and then this is C, and then it's the mid like that, right? So they create the temporary dipoles. Temporary dipoles. In the next slides, in the previous slides, we talk about the permanent dipole. And now we talk about temporary dipoles. So of course it's because a temporary. Okay. I make this. I change this image like that. The deposits. Okay, this is partial positive. I make this is partial negative. Okay, this is a hydrogen with temporary dipole. Hydrogen. Actually, they no have actual hydrogen no dipoles. Hydrogens, okay. But sometimes they have temporary dipoles because this is negative and positive, so this is interact. Make an interaction. But this is a temporary. So of course, because it's a temporary, sometimes it will lose. This is the reason why the van der Waals is the weakest one of bonding, because there are no dipoles of the molecules. If there is a dipoles, it's just a temporary dipoles. When the temporary dipoles is, of course, it's easy to lose. Okay. And the last is hydrogen bonding. Hydrogen bonding is the strongest in secondary bonding. In secondary bonding, hydrogen bonding is strongest. Hydrogen bonding is the three types of bonding between hydrogen and elements with high electronegativity. What is element with high electronegativity? This is nitrogen, oxygen, and fluoride. So some literature, some directly state with the hydrogen bonding is the interaction between hydrogen and nitrogen, hydrogen and oxygen, hydrogen and fluoride. Okay. But why have two nitrogen? Why oxygen? Why fluoride? Why it's not happen with carbon? Why it's not happen with silica? Because hydrogen bonding is interaction with hydrogen and elements with a high electronegativity. Electronegativity is nitrogen, oxygen, and fluoride. This is three bonds all have. Okay, they have two strong permanent dipole. Of course, there is a hydrogen atom over there, and then the atom with lone pair electron. Yes. For the examples, this is hydrogen. This is the molecule. This is the molecule. This is hydrogen fluoride. We are not talking about the types of bonding. No, the types of bonding is covalent bonding. But we talk about the interaction between two molecules. Between molecules, we talk about this interaction. We talk about this interaction. We talk about this interaction. Okay, this is a secondary bonding. If we want to learn about this, if we want to talk about this, we go to the discussion about primary bonding. This is a hydrogen bonding. Okay. Nice. So I make a summary for my explanation. Bonds have a primary. There are two types of bond: primary and secondary bonding. Okay. Could you help me? What is the difference of primary and secondary bonding? What is different of primary and secondary bonding? There are 2 points. In primary bonding, what happened?
Primary bonding, we have to happen the sharing or transfer the electrons.
Okay, that's right. And sharing and transfer. How about the secondary bonding?
There is no sharing and transfer.
Okay. Thank you, Fadli. Electron transfer. This is no sharing. Okay, and the number 2? Anyone? No sharing.
The number 2 would be strong force of attraction for primary bonding.
Okay, strong interaction. Okay. And how about the secondary?
We have weak force interaction.
Weak interaction. Who is the winner in the secondary bonding if we talk about the bond strength?
Primary.
Hydrogen.
Okay, in the secondary bonding. In secondary bonding, who is the winner?
Hydrogen.
Hydrogen bonding. Okay. Who is the weakest in the secondary bonding?
Van der Waals.
Van der Waals. That's right. I have this. If I have molecule, if I have molecule methane, CH4. Okay. What is the type of primary bonding what is the type of primary bonding in methane?
Covalent bonding.
Covalent bonding, that's right. What is the type of secondary bonding that's possible happen in methane? Hydrogen, van der Waals, or dipole interaction? How do you think? I can make a seer. If the example, if HCl hydrogen chloride, make it make it MCl. Okay. If I have a silicon, that's okay. I make it this here. Oops, sorry. Okay. In the primary bonding, what's happened? What types of bonding in between a silicon and oxide? Primary bonding. What type? Ionic, covalent, or metallic bond?
Ionic bonding.
Are you sure with ionic bonding?
Covalent.
Covalent. Why? Why you answer covalent bonding?
Because it has 51% of covalent characteristic and 14.
Oh, thank you so much. Thank you so much. I'm so appreciate because you listen my explanation at first and then the end of slide. Okay, thank you so much. But silicon oxide, this is a covalent bonding. Why covalent bonding? It's not ionic bonding. Ionic bonding is about what? Positive and negative charge. We have two positive and negative charge. But in silicon oxide, no, it's difficult to silicon. It's difficult to silicon become a positive. Why? Because in periodic table, so I have, as I always say, if we talk about the bonding, we have to remember about the periodic table. Okay, I go to the periodic table. Now this is first. Go to the periodic table. Go to the periodic table. You have to clean this. Okay. In ionic bonding, it's about positive or negative. It's possible positive or negative. So we have to choose. We have to predict what is the element can be positive or negative. What is element can be cation or anion. Easy to be cation, easy to be anion. What is the meaning easy to be cation and easy to be anion? Easy to lose electron, easy to lose electron, or easy to gain electron. Too easy to lose an electron, too easy to lose. How do you think? Where is the element? Where is the group of element that easy to lose electron? First, group number 1, 2, or 3, 4, 5, 6, 7. Sorry, 4, 3, 4, 5, 6, 7. What's the number of group that easy to lose electron?
Group 1.
Group 1.
1
and 2.
1 and 2. That's right. 1 and 2. Why 1 and 2 electron? Okay, that's 2. I make okay 3. Okay. Make example sodium. Sodium is okay. Sodium is 11 electron. 11 electron. So this is a 2, 8, and 1. That's right. This is the distribution of electron. This is the electron in the first shell. There are 2 electrons in the second cells, in the 8 electron, and the third cell is 1 electron. So it is easy to lose. Why? Because this is only 1 electron had to lose. Okay. They can go out from the atom because only 1 electron. If there is this, if I have Cl, all right, 17 electron, 2, 8, and 7. How do you think? It is easy to lose or easy to get? The target, the end is to be octet, to have to 8 electron. To 8 electron, so this is have 2 possibilities. Okay, I go to this. All right. Let's see. To be 1 electron. Oh, sorry. 2 possibility. The possibility is 2. Possibility is 2. There are lose 1 electron, or the second possibility is gain 7 electron. Do you understand what I mean? 7 electron. I have to put this. Okay, our target is I move it here. so we can see it clearly. Okay, if sodium with the 11 electron, 2 8 and 1 11 electron, to BH, finally we have to make an octateral. We have to make an octateral. Octateral is 8 electron. So to be 8 electron, the possibility is lose 1 electron to become 2 and H, or gain 7 electron to become 2 H and H. Do you understand what I mean? If lose 1 electron, they become 2 and H, or gain 7 electron, become 2 H and H. Gain 7 electron is 1 plus 7, so totally is 2 8 and 7. Maybe I can use the whiteboard. Sorry. Okay, I can use the whiteboard. This is another sodium with 2 8 1. Okay, the possibility is to be electron rule, to be complete the octet, we can 2 and 8. We have to 8 electron in the valence cell, or 2 H H. Okay, in this 2 and 8, it is lose 1 electron, but in here 2 8 8 is gain 7 electron. Okay, do you understand with this my whiteboard? So how do you think? Okay, so how do you think? Why is the easiest lose 1 electron or gain 7 electrons?
Lose 1 electron.
Lose 1 electron because required how low energy. We only lose 1 electron. Okay, I give you 1 electron. Okay, 1 electron you have to go out from my home. Then you have to invite 7 electron one by one. Okay, the first electron you could first electron come to my house, second electron come to my house, third electron is so required high energy. So the atom is not like with this way. The sodium is not like this way. It's similar with the Cl. It's an example of Cl. Cl is 17. 17 is 2. Oh, sorry, I used another red word. Okay, 17 Cl. 2 H and 7. So to complete the octet rule, to make the electrons, the valence electron is H. So they also have 2 possibilities. How do you think? 2 to become 2 H and
8.
H, or 2 and
8.
8 and H. That's right. And this is gain 1 electron. This is lose 7 electron. So which is the easiest? Gain or lose? Gain 1 electron or lose 7 electron? Why is the way that require low energy? Gain 1 electron or lose 7 electron?
Gain 1 electron.
Gain 1 electron. Okay. Now I'm back to the periodic table. I'm sorry. I got the periodic table. So the ionic bonding is about positive and negative charge. Positive and negative charge, it only happen, it's easy to happen in the group number 1, group number 2, and then number 6, group number 6, and group number 7. Why it's a group number 4 or 5 or number, okay, like that, number 4. Number 4, how about number 4? Okay, number 4, I can see carbon. Carbon with 6. Carbon. Carbon is 2 and 4. Okay, the possibility 2 and H. Here seems 2 and H, but in different mechanism. And here, oh, sorry, not 2 and H. 2, only 2, okay, sorry. Okay. 2 and H, okay. In this, the loss for electron. And this is the gain for electron. Two way effort. Loss for electron is gain for electron. It's a similar require high energy because they have to be C4 plus. So we didn't meet as a C4 plus is C4 plus. C4 means we it's difficult. C4 plus or C4 min is doesn't happen in nature. There is no C4 plus, there is no C4 min in nature, because to lose for electron or gain for electron is required high energy. This is the reason why the C carbon, it's always most of the compounds of carbon is now in the ionic bond, because it's difficult to become positive or negative. This is so difficult. Why? Because required high energy. So in ionic bonds, carbon of ionic bonds is we do not find in nature. So most of them in the covalent bond. Okay. All right. So back to my question. How about silica and oxygen? In the primary bonding, why the type of bonding? What the type of bonding? Ionic or covalent or metallic? Covalent. Because difficult for silica, because difficult to silicon to become positive or negative. And then how about secondary bonding? What type of secondary bonding? There is the option is hydrogen, and then van der Waals interaction, and then permanent dipole. Okay, so how about the secondary bonding? Hydrogen, van der Waals, or permanent dipole interaction? How do you think?
I think permanent dipole.
Permanent dipole, that's right. 100 for you. Hey, permanent dipole. No hydrogen bonding. Why is not hydrogen bonding? Why is hydrogen bonding?
Because it's not attached with oxygen, fluorine, or nitrogen.
Okay, because the simple way, because there is no hydrogen over there. Yes, it's just silicon and oxide, no hydrogen. Okay, and then why is not van der Waals interaction? Because van der Waals interaction only occur on only occur on high. In non-polar molecules, especially in the same element like hydrogen, nitrogen, oxygen, there are no dipole. They only occur on no dipole molecule. No dipole molecule. The interactions is happen because temporary molecules. If there is interaction, wonderful interaction, it happens because a temporary dipole. Okay, temporary dipoles, and then they make interaction, but it's about the temporary. Temporary is not permanent, so almost it's easy to lose. And they have and they become a no dipole anymore. And then because the movement of molecules, okay, and then the temporary dipole is exists. Temporary dipole is exists. Van der Waals is interaction. Van der Waals interaction is happen. But if we talk about temporary, okay, it's back to the no dipole molecules. It's the like a cycles. All right, thank you so much. I hope I think you have. I checked my slides there. I don't know if there is slide anymore or not. I think not. All right, the last slide is thank you. All right, thank you, Siti. I think I'm in the end of slides, so I back to the Siti. Thank you.
All right, thank you so much, Doctor, for an interesting lecture. Now, if anyone has any questions, I'm sure Dr. Alfa would be pleased to answer them. So I will now open for question and answer session.
Hi, Doctor.
Hi, okay.
I want to ask about one question. I don't understand about the ionic bonding. Why lattice energy decrease when the size of ion is increased?
Why the lattice energy is decreased? Okay, when the size ion is
increased.
Oh, increase. Okay. All right. Okay. Okay, Siti, I can answer it or?
Yes, Doctor.
All right. Why the lattice energy is increased when the ion size is decreased? Yes, it's right, Nurul. Yeah. Size is
Why the lattice energy are decreased when size of ion is increased?
okay.
Yeah.
This is okay. Lattice energy. Lattice energy is about the interaction. Okay. Interaction between cation and anion. Cation or anion. Cation and anion. When the ion size is increased, ion size is increased. Okay. You can imagine that about the bonding. If the molecule is increased with the ion size increase, molecule is increased, the interaction is slow. Interaction is slow interaction. If we compare the ion size, the small ion size, okay, the small ion size. This is the The interaction is interaction cation anion is high in a small size. because the interaction, this is in the small size is high, of course the lattice energy is also increased. Okay, this is opposite. This is opposite properties. The lattice energy decrease. Okay, the ion size is increased. Why? Because the ion size. Okay. Like if I have a ball, like a basketball, two basketball. Okay, two basketball. Then I have this. Okay, this is cation. Okay. Wait. This is cation, and this is sorry. Okay, this cation. This is anion. Okay. All right, this is a. This is positive. This is negative. This cation and anion. They have a lattice energy. Oh no. Okay, and I compare with the high cation with the same anion. Okay, the size of anion is same, but this is decreased. This is increased. But the ion size of cation is increased. This is okay. This is a bigger one, and the second is bigger than this is. So I have orange, the fruits of orange. Okay, the fruits of orange, and then one orange, and now this is one of watermelon. Okay. Do you can illustrate in your mind how about the interaction? How about the interaction with two orange, or maybe not orange? This is orange. This is what is the fruit is in bowl? Or apple, orange and apple. Okay, this is orange and apple. Orange and apples. This is orange as watermelon. Orange as watermelon. So how about the interaction? What's one? What's one that have a good interaction? Number one for number two. Apple and orange, or watermelon and orange? How about the good interaction is happening with apple and orange, with the size of apple and orange, or the size of watermelon and orange? How do you think?
Apple and orange.
Apple and orange. That's right. Apple and orange. This is the reason. You will have answered the question. Actually, you answer the question. The lattice energy are decreased. Why decrease? Because the ion size is increased. Why? Ion size increase can make the lattice energy decrease. Yes, because the higher ion size, the higher molecule, the higher ion, the interaction is more lower. Because the interaction is lower, the lattice energy are decreased. Because the lattice energy is talk about the interaction between cation and anion. Okay. I have a tennis ball, and then I have a basketball here. Of course, this is have interaction. Yeah, they have interaction. We can test the clue here. Yes, we can. But how about the strength? How about the strength? Of course, it weak strength. Then we compare with the two ball of tennis, maybe. Yes. Okay. Because the lattice energy is talk about interaction cation anion, so the ion size. If the ions is increased, the ion is increased. So of course the interaction is become lower. So the consequence is lattice energy are decreased. Nurul, how about my explanation?
I understand it. Thank you.
Thank you so much, Nurul. Okay.
Is there any other questions?
I have a question.
Yeah.
Hello, Doctor. My name is Adlina Mutujahari, and I got one question for you. Basically, what Doctor mentioned earlier is magnesium oxide have the ionic bonding, which is composed of 70% of ionic character. But then it also have 30% of covalent character. So what basically makes this compound have this covalent characteristic? Is it because of the characteristic that this compound have that make it to be the have this covalent characteristic? Okay, that's all.
Okay, that's right. Okay, here. This is about the ionic covalent and character. Ionic covalent character. Magnesium oxide. This is an ionic solid. Ionic bonding. The bonding is ionic. So this is ionic solid. But the character, the character is the properties. They have the properties of ionic. They have the properties of character, or you can say character properties. Character or properties. They have ionic properties and covalent properties. Okay, why it's happened? Because actually there is no. If we talk about the bonding, only ionic or covalent or metallic, we talk about the bonding. So here, okay, I was to slide, go to the slide. Where is okay. Ionic covalence bond. Okay, it's about the character. It's about the character. The character of ionic, the magnesium oxide. The type of bonding is only ionic. The type of bonding is only. But the character, the properties, they also have covalent properties and ionic properties. Why? Because it's happened because they have, this depends the electronegativity. This depends the electronegativity. The electronegativity X, this is the electronegativity A, this is the electronegativity B. This is the electronegativity of Mg, magnesium. This is the electronegativity of oxygen. Why? Because this is the electronegativity is okay. You can see like that is 1A. If ionic character 100%, okay, we go to the formula. We want sorry. If we go to the formula, if we want to character is 100%, the value of this, okay, is have to become 0. This is right. Become a 0. Okay. I repeat my explanation. If we want to ionic character is 100%, if one ionic character 1%, almost this is the formula, the equation must be 1 multiple 100%. Yes. So the value is 100%. To be 1, this. So the value this is always it's have to 0. It must a 0. 0. But it's 0 is possible. It's not. How about the 0? 0 is mean that the electronegativity is 0 is we can the result is impossible to be 0. Why? Because the electron, why? Because the atom have a value in the electronegativity, have the value of electronegativity. Although we have a sodium and chloride, although we have a sodium and chloride is, this is group number 1, this is group number 7. This is easy lose electron. This is easy to gain electron. Compared with magnesium oxide is they have to lose 2 electrons. Oxygen they have to gain 2 electrons. If we compare with sodium chloride, of course, it is more ionic. But because there is a value here, this is electronegativity is have a value. So is it impossible? We make it the value this is a 0. It means this impossible. We get a 100% ionic. Because the electronegativity, because the element have an electronegativity. Okay, I repeat. Why it's happened? Because the atom have electronegativity. This is the answer. Why it's happened covalent? Why 70% and 30%? It's because there is a value of electronegativity between Mg and O, and magnesium and oxygen. Once again, and when we decrease the value of electronegativity value of magnesium and oxygen, okay, we have some value, and then this value we calculate that, and we found the 70.2%. Why it's happened? Because because the atom have electronegativity. If the atom can no electronegativity, maybe it can be results. It can be we can get the value. Is this the 0? And then if the 0, 1 decrease 0, and so the result is 1. 1 multiple 100% is the character ionic is 100%. But it's impossible because each element have electronegativity. Okay, Adrina, could you understand? Also, I recommend to all of you to browse the topic about the ionic covalent bonding. It's interesting. It's interesting. Or maybe if we have time, you can email me. You can you can chat in my WhatsApp. We can discuss more on the time. Talk about ionic covalent bonding. Siti have my number handphone, so you can discuss anytime to talk about the ionic covalent bonding. Okay, Adlina, you understand?
Yes, doctor. Thank you.
All right. This is about the value of electronegativity. All right. Is there? Siti?
All right. Thank you, Doctor. Is there any more questions from everyone else? All right. If there is no more questions, thank you very much, Dr. Alfa, for your valuable sharing today, as well as your contribution in today's lecture. I would like to thank you from the bottom of my heart for taking time for your busy schedule to be the guest speaker at this lecture today. So before we jump to the photo session, may I invite our lecturer, Dr. Shi, to give a speech.
All right, thank you. By the way, thank you so much for your active presentation for the all of participants. Thank you so much. Actually, in Surabaya, it's 4 p.m. And here, over there, 5 p.m. This is 5 p.m.
5 p.m.
Okay. Thank you so much for your active presentation. I'm so very glad to be your teacher for one day, to be a lecturer for one day. I'm proud of all of you, student. What year? The participants is undergraduate. Student, undergraduate student for.
Yes, but
Yes.
We are undergraduate.
Okay, that's right.
Okay. I'm so sorry. I'm having problem with my mouse just now. So I would like to say thank you very much. Thank you very much. Thank you very much to Dr. Alfa. Thank you.
Welcome, doctor.
For your lecture, for entertain my students. So actually they are undergrad student, Dr. Sasi. Dr. Alfa.
Yeah.
Yeah, they are undergrad students, and they are right now in semester 5.
Okay. They are active participant, doctor. So
Yeah.
I'm so glad. I'm so proud with your student.
Yeah, thank you very much, doctor. So everyone, maybe inshallah I will invite you again, Dr. Alfa, for next semester for this topic, because I think that you are so expert explaining. You are very expert in this topic, and I do believe that all my students are really enjoy listening to your lecture.
Thank you. I hope